This is Physics 2120, Lecture 24, and today we're going to talk about light and geometric optics, specifically reflection and refraction. So before the beginning of the 19th century, light was considered to be a stream of particles. And the particles were either emitted by an object being viewed or maybe emanated from the eyes of a viewer. Actually, Isaac Newton was the chief architect of the particle theory of light. He believed the particles left the object and stimulated the sense of sight when they entered the eyes. Christian Huygens argued that light must be some sort of wave motion, and certainly Thomas Young in 1801 provided the first clear demonstration of a wave nature of light. Essentially, he showed that light rays interfere with each other, and you can't get that type of behavior explained by particles, only by waves. During the 19th century, other developments led to the general acceptance of the wave theory of light. And of course, we've learned last chapter that Maxwell asserted that light was a form of high-frequency electromagnetic waves, and Hertz confirmed Maxwell's predictions. However, some experiments could not be explained by a wave nature of light. The photoelectric effect was a major phenomenon that was not explained by waves. When light strikes a metal surface, electrons are sometimes ejected from the surface. And the kinetic energy of the ejected electron is independent of the frequency of light, so it must also be particle-like. And Einstein in 1905 proposed an explanation of the photoelectric effect that used the idea of quantization. The quantization model assumes that energy in a light wave is present in particles called photons, and that the energy of a photon is hf, where h is Planck's constant, 6.63 times 10 to the minus 34 joules seconds. The frequency is just the frequency of the light. So, in view of these developments, light must be regarded as having a dual nature. Light exhibits the characteristics of a wave in some situations, and the characteristics of a particle in other situations. And nature really prevents us from testing both quantities at the same time. We'll look at this more in depth when we start learning about modern physics next semester. Since light travels at a very high speed, early attempts to measure its speed were unsuccessful. Remember that the speed of light is 3 times 10 to the 8th meters per second. Galileo first tried measuring the speed of light by having two observers separated by 10 kilometers on two different hills. And one observer would take a cloth off of a light and shine it, and the other observer, when he saw the light, would take his cloth off, and the first observer then would measure the amount of time it took. And this was really a measure of the reaction time of the observers more than a transit time of the light, but it certainly gave a lower limit on the speed of light. And Ole Romer in 1675 used astronomy to estimate the speed of light. He used the period of revolution of Io, which is the moon of Jupiter, as Jupiter moved around the sun. The periods of revolution were longer when Earth was receding from Jupiter, and shorter when Earth was approaching. And using Romer's data, Huygens estimated that the lower limit of the speed of light has to be 2.3 times 10 to the 8 meters per second. This was really an important result because it demonstrated that light had a finite speed as well as giving an estimate of that speed. Fizeau's method is the first successful method for measuring the speed of light by a terrestrial technique. It was developed in 1849 by Armand Fizeau, and he used a toothed wheel. And we have a distance between a wheel, which is we're going to consider the source of light, and a mirror. And so, as light comes, in this case it's going to strike a partial mirror, and it's going to go this certain distance here to a mirror and back, and as your eye is watching it, we're going to see that we can either see the light in the tooth or we can't see the light on the tooth depending on the speed of the toothed wheel. So, d is the distance between the mirror and wheel, delta t is the time for one round trip. And we know that the speed of light then is twice the distance over the time it takes. And so as light would come through the tooth wheel, would strike a mirror and come back. If the wheel was moving at the right speed, the next tooth would block the light from from being able to be perceived. However, if the wheel was going slightly faster, the next opening would come in and we could see the light. And Fizeau, using this method, found a speed of light of 3.1 times 10 to the 8th meters per second. So let's look at a problem using Fizeau's method. Let's assume that Fizeau's wheel has 360 teeth and is rotating at 27.5 revolutions per second when a pulse of light passing through point A is blocked by point B on its return. If the mirror is 7.5 kilometers away, what is the speed of light? So first, we know omega is delta theta over delta t. So then, therefore, delta t, or the time it takes for that tooth to revolve into place, it's going to be the angle divided by omega. The angle is 1 over 720 revolutions, because it has 360 teeth. So that means that there are 720 segments between an opening and a closing. Omega, we said, is 27.5 revolutions per second, so that means that the time it took for the light to go there and back is 5.05 times 10 to the minus 5th seconds. We can then measure the speed of light. It's 2d over delta t. So that's 2 times 7,500 meters over a time we just calculated, and we get 2.97 times 10 to the 8th meters per second. Now, as we start studying geometric optics, what that is a study of propagation of light through different medium. We're going to make the assumption that light travels in a straight line path in a uniform medium and changes direction when it meets a surface of a different medium, or if the optical properties of the medium are non-uniform. And a ray approximation is used to represent beams of light. The rays are straight lines perpendicular to the wavefronts of the light. With the ray approximation, we assume that a wave moving through a medium travels in a straight line in the direction of the rays. If a wave meets a barrier, we'll assume that the wavelength of the wave is much, much less than the diameter of the opening of the wave. And this is a very good approximation to study mirrors, lenses, and prisms and things like that. Later on, we'll talk about what happens when the wavelength is on the size of any openings. So a ray of light, which we'll call the incident ray, travels in a medium. When it encounters a boundary with a second medium, part of the incident wave is reflected back into the first medium. So that means it's directed backwards into the first medium. Specular reflection is reflection we get from a smooth surface. The reflected rays are all parallel to each other. All reflection in this text is assumed to be specular. Diffuse reflection is reflection from a rough surface. The reflected rays travel in a variety of different directions. And so the surface behaves as a smooth surface as long as the variations are much smaller than the wavelengths of light. So if we look down here at this piece of glass here, it's got a rough edge. If we look microscopically what the edge looks like, it might have lots of divots and bumps. So as the light comes, it's going to reflect in different directions off of every part, and that's diffuse reflection. We see that the light beam doesn't continue off. Light goes in all different directions. So we'll start with understanding the law of reflection. And so in order to understand that, we need to define some concepts. The normal to a surface is a line perpendicular to the surface. We draw it at the point where the incident ray strikes the surface. And then the incident ray is going to make an angle, say theta 1, with the normal. The reflected ray makes an angle theta 1 prime with the normal. So when we're measuring angles, we're always going to measure angles from the normal, not from the surface, but from the normal. The law of reflection states that the angle of reflection is equal to the angle of incidence, or theta prime is equal to theta. The incident ray and the reflected ray also lie in the same plane as each other and in the same plane of the normal. So I can have multiple reflections. In this case, maybe I have an incident ray strikes the first mirror, it comes off, it's directed towards the second mirror, and then there's a second reflection off this. In order to solve a problem like that, we apply the law of reflection to any point where the light is reflected. Now, I can also develop something called a retroreflection. If I assume the angle between two mirrors is 90 degrees, then the reflected beam returns to the source parallel to its original path. It's called retroreflection. You can see this in sort of everyday things. If you look very closely at a stop sign and you look at it, there will be small bumps on it. And if you look in the bumps, all the bumps appear to be the inside of a cube. So I have three surfaces that are all perpendicular to each other. That way, any light that comes and strikes the stop sign comes right back, and we're able to see the stop sign better. Or if you look at the reflectors in the back of new vehicles, those little dots that we see in here actually look, again, like the inside of a cube. On the moon, the Apollo astronauts put a very good retroreflector. They have three mirrors that are all 90 degrees from each other. And that way, if I shine a laser at the moon, it's going to come exactly straight back at it, and we're able to use this retroreflector to measure the distance between the Earth and the moon to within a few centimeters. So let's look at this double reflected light ray, and let's see how we apply this. Two mirrors make an angle of 120 degrees. A ray is incident on mirror 1 at an angle of 65 degrees to the normal. If M1 lies flat on a level surface, what direction does the ray reflected from M2 point? So, we're going to use a law of reflection, and we're going to go through this step by step. So first, the light coming in is reflected at the same angle, so it's 65 degrees off of mirror 1. So, because of that, we can figure out what this angle is here, because the normal we said is at 90 degrees. So if this was 65, this angle is 25. We know this angle is 120, we know this is 25, so from geometry we know that the sum of all those angles is 180, so we know that this angle is 35. And since, again, this is a right angle, we know that the next angle here is 55 degrees. And from the law of reflection, we know that the reflected is also at 55 degrees. Now, then we also know as we continue this line out that this angle right here is 35 degrees again. Because again, this is 90-degree angle. Now I can form a triangle here on the bottom. If this was 120 degrees, I know this angle is 60 degrees. And I know that this angle is 35 degrees because I have this line and this line, so I've got opposite angles that have to be equal to each other. So if this is 60 and this is 35, I can measure this down here is 85 degrees. If 85 degrees, then this angle here is 5 degrees. And so the reflected ray is 5 degrees to the left of straight up and down. Now, when a ray of light travels through a transparent medium and it encounters a boundary going into another transparent medium, part of the energy is reflected and part of it actually enters the second medium. The ray that enters the second medium is bent at the boundary, and the bending of a ray is called refraction. The incident ray, the reflected ray, and the refracted ray and the normal are all going to lie in the same plane. And the angle of refraction depends on the material and the angle of incidence. We know that sine theta 2, that's the refracted angle, over sine theta 1, which is the incident angle, it's going to be the same as the difference of the velocities of light in those two substances, which is going to be a constant. So for example, as I have light coming in air and strikes a glass surface. So as it comes, part of it is going to be reflected, and that's going to obey the law of reflection that we just talked about. But part of it's going to be refracted, and so the light ray is actually bent. In this case, it's bent more towards the normal than it would if it just were to continue straight through. So in this figure, ray 1 is the incident ray, ray 2 is the reflected ray. Ray 3 here is refracted into the lucite. And here ray 4 is, there's an internal reflection in the lucite as the light is reflected back up towards the surface. And then ray 5 here is refracted again as it goes from the air from the lucite. So light can refract into a material where its speed is lower. For example, the speed of light in glass is less than that in the air. If that's the case, then the angle of refraction is less than the angle of incidence. The ray bends toward the normal when going from a high speed to a lower speed substance. But light can also refract into a material where the speed is higher. In that case, the angle of refraction is greater than the angle of incidence. So as light's coming inside glass out into air, the ray bends away from the normal. So why does light move at different speeds in a medium? Let's look at light entering from the left. Light in here can encounter an electron. That electron can absorb the light, can oscillate and re-radiate the light. And the absorption and radiation cause the average speed of light moving through the material to decrease. So here we have a laser going through glass, maybe from air into glass into air. And so the incident ray comes down and it hits the normal, and since medium 2 has got a higher index of refraction, it means the speed of light is slower, it's bent towards the normal. And then as it comes back out of the glass into air, it's bent away from the normal. So the speed of light in any material is going to be less than its speed in a vacuum. The index of refraction, N, of a medium is then defined as the speed of light in a vacuum divided by the speed of light in the medium, or C over V. So N is always going to be a number greater than 1. For a vacuum then, N is going to be 1. And we're going to use N equals 1 for air. It's actually slightly more than that, but the difference is so slight that we can neglect it. But for all other media then, N is going to be bigger than 1. N is a dimensionless number, greater than 1, but not an integer. So we can see then that some substances, light really changes a lot of speed. For example, in diamond, the index of refraction is 2.4. That means that light is moving almost 2.5 times slower in diamond than it does in air. Or gallium phosphide, 3.5. We have index of refraction for liquids too. For water, it's 1.33. This is why light's going to bend when you're looking through water, say in an aquarium or something. Even gases slow down light a little bit. Air, we said, is essentially 1. It's actually 1.000293. So for our calculations, we can assume it's 1. But it's different than air than, say, just pure carbon dioxide. And all these values here are for light having a wavelength of 589 nanometers. The index of refraction is actually going to be slightly different for light of different wavelengths. So as light travels from one medium to another, its frequency does not change. Remember, we learned from Einstein that the energy of a piece of light, a photon, is hf. if the frequency changed, the energy would change, and we would have to leave that energy somewhere, and we can't lose energy in these cases. So the frequency has to stay the same. However, the wave speed, and therefore the wavelength, does change. The wave fronts don't pile up. They are not created or destroyed at the boundary. Therefore, F must stay the same, or else you would have a buildup of waves at one boundary. So the frequency stays the same as the other wave travels from one medium to the other. We know that velocity is frequency times wavelength, and that the frequencies are the same. We also know that V1 is bigger than V2, so lambda 1 is going to be bigger than lambda 2. So the ratios of the indices of refraction of the two medium can be expressed also as the ratio of the wavelengths, but it's inversely proportional to the ratio of the wavelengths. Lambda 1 over lambda 2 is equal to N2 over N1. So the previous relationship can be simplified to compare wavelengths and indices. Lambda 1 N1 is equal to lambda 2 N2. And in air, we know that N1 is much bigger than 1, and the index of refraction of the other material can be then defined in terms of the other wavelengths. So N is lambda over lambda N, where lambda is the wavelength in a vacuum, lambda N is the wavelength inside that medium. Now, Snell came up with a law that explained how refraction works. N1 sine theta 1 is equal to N2 sine theta 2. Theta 1 is the angle of incidence, and N1 is going to be the index of refraction of that material. Theta 2 is called the angle of refraction. The experimental discovery of this relationship is credited to Wilbrod Snell and is therefore known as Snell's law of refraction. So let's look at an example. Light's refracted into crown glass. We know the incident angle is 30 degrees. We don't know what the refracted ray is. We know N1 is air, so it's going to be 1.0. And N2 for crown gas is 1.52. So, solving Snell's law, theta 2 is the inverse sine of N1 over N2 times sine theta 1. We plug in these values given and we get 19.2 degrees. So the ray bent towards the normal just as expected. Let's look at another problem where we're going to measure the index of refraction. A beam of light of wavelength 550 nanometers traveling through the air is incident on a slab of transparent material. The incident beam makes an angle of 40 degrees with the normal. The refracted beam makes an angle of 26 degrees with the normal. Use our table 35.1 to determine what the transparent material is composed of. So we start with Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. We solve for N2, and then we plug in our values. N1 was 1, sine of 40 over sine of 26, and we get 1.47 is the index of refraction of this material. So we go to our indices of refraction, we go up and down, we see it could be several different things. The closest, though, we're going to say is fused quartz, 1.46. So, to review what we talked about today, we talked about light, that it has both a particle and a wave-like nature. We talked about the law of reflection, and how we can use the ray approximation to figure out that the incident angle is equal to the reflected angle. And we talked about refraction, how light rays bend as they go from one medium to another, and Snell's law of refraction gives us a way of calculating how much something is bent.